scroll through a feed by a ticket. How often do you actually stop and think about how incredibly fast these things respond? It feels almost instant, doesn't it? Even when there's potentially millions of pieces of data flying around behind the scenes. So what's the secret? What's the magic that makes an API that's the application programming interface feel so snappy, so efficient, delivering what you need right when you need it? Well, today in this deep dive, we're going to try and pull back the curtain on that a bit. We're going to explore, let's say, the top 5 common strategies developers use to really boost API performance. Think of it as a shortcut to understanding how some of the fastest digital experiences you use every day are actually built.
Yeah, and it's interesting because it's not just about raw speed, although, that's obviously great for you, the user. Optimizing API performance is really fundamental. It's about resource efficiency for the companies building these things. It lets them scale up, handle huge amounts of traffic, and ultimately it's about giving you that smooth, frustration-free experience you kind of just expect now.
Okay, so let's dive into the first one. Strategy number 1 is result pagination. So paint the picture. What happens if an API tries to send you, I don't know, thousands, maybe even millions of records all in one go? What does that look like?
Chaos, basically. Yeah. Chaos is the right word. I mean, the fundamental problem is you just completely overwhelm memory, network bandwidth, everything. So what pagination does is it breaks those massive results down into manageable chunks or pages. It usually uses simple query parameters like limit to say, give me this many items, and offset to say, start from here. The benefits are pretty clear, right? It drastically cuts down memory use, both on the server and on your device. It makes the response time way better because smaller chunks just load faster. And crucially, it helps these systems scale up to handle enormous data sets because they're not trying to shove everything through the pipe at once.
That makes total sense for just breaking things up. But I've heard there are different ways to do pagination beyond just that simple limit and offset. What are some of those other methods? And why pick one over the other?
Oh, absolutely. Yeah, the simplest, as you said, is offset-based, that offset 100 and limit 50 kind of thing. It's easy. Developers get it quickly. But the drawback, it can get really inefficient if you're trying to get to, say, page 500 of a million records. The database often still has to kind of count through all the records you're skipping just to find where page 500 starts. That can get slow.
Ah, okay. So it's like counting from 1 every time, even if you want item million.
Sort of, yeah. It depends on the database, but that's the risk. Then you've got cursor-based pagination. This uses a sort of opaque token, a cursor, that basically points to the last item you fetched. This is brilliant for things like real-time feeds or infinite scrolling where new items might be added while you're looking.
Right, because it doesn't rely on fixed page numbers.
Exactly. You're always just asking for the next 50 items after this specific one. It handles changes much better. And then there's also keyset pagination. This is really powerful, especially if your data is sorted nicely, like by a unique ID or a timestamp. It uses the actual value of the last item's sort key, like the ID or the timestamp, to fetch the next batch very efficiently. It avoids those full table scans that can sometimes plague offset pagination.
Okay, so you've got these different technical approaches: offset, cursor, keyset. When you boil it all down, what does this actually mean for, us using apps every day?
For you, it translates directly into that feeling of a smooth, endlessly scrolling social media feed, or getting search results back almost instantly when you're shopping online, or just less waiting around when an application needs to load a bunch of information. It's kind of the invisible plumbing making things flow nicely.
Okay, cool. So from delivering data smoothly, let's pivot a bit. Let's talk about what happens behind the scenes. Our next strategy, asynchronous logging. Applications are constantly recording what they're doing, right? User clicks, errors, data changes from debugging, security, analytics, all that stuff. But the question is, how do they log all that vital information without actually slowing down the main thing you're trying to do?
Right. And this is a classic bottleneck if you're not careful. The core idea with asynchronous logging is decoupling. You separate the act of logging from the main request your app is handling. So instead of making the API wait while it writes a log message to a disk, which can be slow, or sends it to some external system, the log message gets fired off really quickly into, say, an in-memory buffer or a queue. This lets the API finish its main job and send the response back to you immediately. It doesn't get blocked waiting for the logging to finish.
So the API's main job responding to me isn't held up by the need to write stuff down. You mentioned this helps ensure non-blocking I/O and makes things more responsive. Can you unpack non-blocking I/O a bit more? Why is that so important here, beyond just the logging itself?
Yeah, good question. So I/O is input-output. Think writing to disk, sending data over the network. If an operation is blocking, it means the main application thread, the part handling your request right now, literally stops and waits for that I/O to finish before doing anything else.
Okay.
If that thread is blocked writing a log, it can't handle the next person's request coming in. Everything grinds to a halt if traffic is high. Non-blocking I/O means the API says, okay, background task, handle this log, and immediately frees up its main thread to grab the next incoming request. It's all about keeping that main path clear to handle as many users as possible concurrently. It boosts throughput massively.
Got it. So it's like having a separate helper handling the paperwork while the main person keeps serving customers. Are there specific tools or, common ways developers implement this?
Oh yeah, definitely. In practice, you often see log queues messages just pile up temporarily, and then background worker threads or processes pick them off the queue and handle the actual writing. You've got tools like Log4j2's async appenders in the Java world, or libraries like Winston for Node.js, StructLog for Python. They're all built around this async concept. I remember a project years ago. We thought our logging was fine. Then we had a huge traffic spike, and suddenly API responses just tanked. Horribly slow. Turned out our synchronous logging was the bottleneck. It was like a single lane road during rush hour. Switching to async logging, putting logs in a queue made a night and day difference.
Wow. So for us users, this means when things get busy, like during a sale or a big event, when you hit submit or refresh, your request doesn't get stuck in a queue behind a million log entries. It just goes through quickly while the system still manages to record everything it needs to behind the scenes.
Precisely. It keeps things feeling responsive even under heavy load.
All right, strategy number 3. Data caching. This one feels intuitive, right? It's about getting information you need frequently to you faster. The basic idea seems simple. Don't keep asking the database the same question over and over if you already know the answer.
Exactly. That's the core principle. You store data that's accessed a lot. Think user profiles, maybe product catalogs, configuration settings in really fast memory. Often this means using dedicated systems like Redis or Memcached, which are basically super fast key value stores running in memory. And the benefits here are pretty dramatic. First, response times get way faster, often down into the millisecond range because you're just pulling data from RAM instead of hitting a slower disk-based database. Second, it hugely reduces the load on your main database. Fewer queries hit it, which is better for its health and performance. And third, that can actually lead to real cost savings, especially if you're using cloud databases where you might pay per query or per hour of compute time. Less load often means less cost.
Okay, that sounds amazing for speed and saving resources, but it feels like there must be a catch. Like getting that instant speed seems like it could introduce complexity somewhere else, maybe around keeping the data up to date.
You've absolutely hit the nail on the head. That's the hidden complexity, the real deep dive challenge with caching. While it speeds things up like crazy, you introduce this new problem, cache invalidation. How do you make sure the data in the cache is still fresh and matches what's in the main database?
Right, because the database data could change.
Exactly. If your database gets updated, but your cache still holds the old version, you end up showing stale, incorrect information to users. And figuring out when and how to update or remove stuff from the cache, that's notoriously tricky. Developers spend a lot of time designing strategies for cache expiration, for updating it correctly, especially when multiple things might be changing at once. It can honestly be harder than the original speed problem they were trying to solve.
So it's not just having a cache, it's managing its life cycle really carefully. Okay. So where can this caching actually happen? Are there different levels?
Yeah, there are several places. You can have client-side caching right there in your browser. Your browser uses things like local storage or just standard HTTP cache headers. The server tells your browser, hey, you can hang on to this image for a day.
Okay, so my browser doesn't even ask the server next time.
For a while, yeah. Then there's server-side memory caching. This could be simple caches inside the application process itself, or more commonly those external stores we mentioned, like Redis or Memcached, that multiple servers can share.
Makes sense.
And finally, you've got distributed caches, which can be spread across many machines, often working hand-in-hand with content delivery networks or CDNs. CDNs are great at caching static files like images or videos, but they can also cache API responses physically closer to you around the world. A really common pattern developers use is called cache-aside, or sometimes lazy loading. The application first checks, is the data I need in the cache?
If yes, great, use it.
Exactly. If no, then it goes to the database, fetches the data, puts it into the cache for next time, and then finally returns it to you.
Gotcha. So it only hits the database when it absolutely has to.
Right. And the difference for you is stark. Imagine loading your profile page. If it's cached, boom, it's instant. If not, you might see that little spinner while it queries the database. Caching makes more things feel like boom.
Okay, let's shift gears again, from data storage to data transfer. Strategy 4, payload compression. This sounds like it's about making the data packets themselves smaller as they travel across the network. Less data equals faster travel.
That's precisely it. You use clever algorithms. Gzip and brotli are the common ones you hear about to basically shrink the size of the request and response bodies. This is especially effective for text-based data like JSON or XML, which often have a lot of repetition that can be compressed really well. The benefits? Well, first, less bandwidth usage. That can actually save companies money on data transfer costs. Second, faster communication between your client device and the server, simply because there's less data to physically send and receive. And third, and this is really important, it means much better performance for you if you're on a mobile network or maybe just a slower Wi-Fi connection where bandwidth is limited. There is a small trade-off. Compressing and decompressing takes a tiny bit of CPU power on both ends, but for anything but the smallest payloads, the network savings usually win out by a huge margin.
So how does this actually work in practice? Like, how does my browser know the server can send compressed data, and how does the server know my browser can handle it?
It's usually handled automatically using standard HTTP headers. It's quite neat, actually. Your browser sends a header in its request called accept encoding. It basically lists the compression types it understands, like gzip, deflate, brr.
Telling the server what it can handle.
Yep. Then the server, if it's configured to use compression and sees a format it supports in your request, will compress the response data. And critically, it sends back a header called content encoding, saying something like content encoding.gzip. Your browser sees that, knows the data is gzipped, and automatically decompresses it before rendering the page or using the data. It all happens transparently to you.
Ah, clever. So it's a negotiation that happens automatically.
Pretty much. And implementing it, often it's done at the web server level. Things like Nginx or Apache are really good at doing this efficiently. Or developers can use middleware directly in their application frameworks, like in FastAPI for Python or Express.js for Node to handle the compression. But yeah, for you, the user, it's totally invisible, just part of what makes the modern web feel fast.
All right, final strategy. Number 5, connection pooling. Now, I didn't really thought about this before, but setting up a connection to a database, that actually takes time and resources, right? It's not instantaneous.
Oh, absolutely not. Establishing a new connection to a database involves network handshakes, authentication, setting up the session. It's surprisingly expensive in terms of time and server resources. If your application had to do that whole dance for every single incoming request that needed database access, things would slow down dramatically, especially under load.
So connection pooling fixes that.
It does. The idea is simple but powerful. Instead of creating a new connection every time, the application maintains a pool of already established, ready-to-use database connections. When a request needs the database, it just borrows an available connection from the pool.
Uses it
to run its queries, gets the data it needs.
and then puts it back.
Exactly. It returns the connection to the pool, making it available for the next request. The benefits are huge. First, you eliminate that connection setup overhead for most requests, which drastically cuts down latency for database operations. Second, it allows for better concurrent access to the database because multiple requests can use the available connections in the pool simultaneously. And third, overall, it significantly improves the API's throughput, how many requests it can handle per second, by managing those database resources much more efficiently.
I've seen configurations for this in code sometimes. Like in Python with SQLAlchemy, you see settings like pool size or max overflow.
Yeah, exactly. Pool size tells it how many connections to keep open and ready in the pool normally. Max overflow often allows the pool to temporarily create a few extra connections if there's a sudden spike in demand beyond the normal pool size. And pool recycle is important too. It makes sure connections don't get stale or dropped by the database or firewall if they sit idle for too long. It automatically replaces old connections with fresh ones.
Right, keeping the pool healthy.
Yep. And this isn't just a Python thing, obviously. It's fundamental everywhere. Java has incredibly optimized pools like HikariCP. Node.js has things like pgpool for PostgreSQL.
Yeah.
Every major language and database ecosystem relies on connection pooling.
That sounds like another one of those balancing acts for developers. How do they figure out the right size for that pool? Not too small, not too big, What happens if they get it wrong?
That is a classic tuning problem. You're absolutely right. It's about finding that sweet spot. If the pool is too small, requests will have to wait for a connection to become free. You'll see increased latency, maybe even timeouts under high load, because requests are just queuing up waiting.
Okay, so too small is bad. What about too big?
Well, if the pool is way too big, you might be holding open lots of database connections that are just sitting idle most of the time. Each connection consumes memory, both on the application server and on the database server itself, so you're potentially wasting resources. And in extreme cases, having too many connections open could even overwhelm the database server, causing its performance to degrade for everyone. Resource exhaustion.
So how do they find the balance? Just guess.
Well, you start with some reasonable defaults based on expected load, maybe recommendations for the database. But then, crucially, you monitor. You watch the application under realistic load. You look at metrics like how long are requests waiting for a connection? How many connections are active versus idle? How's the database CPU and memory looking? And then you tune iteratively. Maybe increase the pool size slightly, test again, decrease it, test again. It's often a process of observation and refinement to find that optimal point for that specific application and workload.
Makes sense. Constant monitoring and tweaking. Okay, so let's quickly recap this deep dive. We hit 5 key strategies for boosting API performance. We started with result pagination, breaking up big data sets, which helps memory and makes the user experience smoother.
Right, delivering data in manageable pieces.
Then asynchronous logging, decoupling the logging process to reduce latency and stop logging from blocking the main application flow.
Keeps the main path clear, especially under load.
Third was data caching, using fast memory like Redis to serve common requests instantly, taking load off the database, but with that tricky challenge of keeping the cache fresh.
Speed versus consistency, the eternal trade-off.
Fourth, payload compression, shrinking data with gzip or brotli for faster network transit, especially vital on slower connections.
Less data, faster travel. Simple but effective.
And finally, connection pooling, reusing database connections to slash overhead and boost throughput significantly.
Avoids that expensive connection setup dance. And, it's really important to remember these things usually don't work in isolation. A really high-performing API is often using several, or maybe even all, of these techniques together. They complement each other. Caching reduces database hits. Pooling makes the remaining hits faster. Pagination manages the result size. Compression speeds up the network transfer. It's a synergistic effect. Applying these techniques thoughtfully is how developers build those really smooth, really fast digital experiences that you've come to expect. Maybe now you understand a little bit more about how they do it.
Definitely. So here's a thought to leave you with. Now that you've peeked behind the curtain at these kinds of optimizations, pagination, caching, pooling, and the rest, how might that change how you perceive the apps and websites you use every single day? When something feels incredibly fast, or maybe sometimes when it feels a little slow, what other invisible performance tricks might be at play, powering the digital world all around you? Something to think about. We hope you keep that curiosity going and continue exploring the fascinating, complex systems that make all this modern tech work.